there. Okay. So sorry for Monday, but we will have our 3 classes this week. The other is tomorrow, and then on Friday. I will start to share my screen so we can discuss. So you see my lecture notes now? So in the last lecture, we discussed the ENSO teleconnections and feedback mechanisms in the Pacific in principle. As is probably true for all of these chapters that we discuss, there are whole books written about ENSO and ENSO teleconnections and the mechanisms and so on. So that is generally the case. So there's much more material than we can cover in this course. This was just to give some basic ideas what we can quickly understand as feedback mechanisms for the ENSO phenomenon, and that's supposed to be just to give some insights in if someone is interested to study further later on, or if you go into that field. But this will be true for all the chapters of this course, I think. Now, so one of the things is that we have learned is that ENSO has globally has locally this positive feedback, this Bjerknes feedback that is there for the mean state, and that can be relevant also then for the also for ENSO and La Nina and El Nino phenomenon, where this Bjerknes feedback also works and acts as a positive feedback, as we have shown. Now, remotely, ENSO can have global impacts on temperature and rainfall. And we will come back to this point many times. So the reason for the lecture today, which covers the boundary layer, some features of the boundary layers, is essentially to introduce one mechanism how El Nino and La Nina can introduce global remote, let's say remote teleconnections. And that mechanism that we want to highlight by looking at boundary layer processes is the Ekman pumping mechanism. So a vertical velocity induced by low-level convergence or divergence, a vertical velocity that is created on top of the atmospheric boundary layer through this Ekman pumping mechanism. That is one of the mechanisms how ENSO now can create remote impacts on rainfall. And we will discuss this in more details also in tomorrow's lecture, how this exactly works. But that is the main reason for discussing the lecture today. So if I say planetary boundary layer processes, really the main aim is here to introduce this Ekman pumping mechanism. Now look at this feature here. I think it is not very well chosen, because I think if you look at in current weather, we are looking frequently at this windy page. And I think on that, when windy is this website where you can have animated weather maps with wind vectors on top of pressure maps, and there you probably can see much better that there is a tendency, if you look at a surface pressure map, and then you see, for example, here, this is a mean state in the North Pacific. So we have this Aleutian low situation, and the winds, as we know, should rotate according to the geostrophic balance in a certain way around this low pressure, exactly in this anti-clockwise sense. And And that is what we see in principle. However, if you pay careful attention, there seems to be a systematic angle between the surface winds and the lines of constant pressure. So there is some, and if you look at this carefully, there's some inflow into this low pressure here. And that is due to, we believe, processes in the atmospheric boundary layer in this case. But if you look on a windy daily weather map, maybe somewhere over land, over Asia, you will see this on a day-by-day basis. If there's a high pressure system, the air is typically flowing out of that high pressure system. Or if you have a cyclone, the air is flowing into the cyclone. There can be other processes that makes the cyclone and anticyclones do this if they are developing quickly, for example. But these boundary layer processes, they're very important contributions in the lower atmosphere. We have also discussed this when we discussed the trade winds. Remember, the trade winds, they blow on average, then we should go further to the south here, when we have the subtropical high system, but they should, according to geostrophic balance, if there's a high pressure in the subtropics and a low pressure at the equator, then the trade winds should blow from the east to the west. But in reality, they blow from the northeast to the southwest. So there's also convergence at the equator due to the trade winds. And this is what we want to understand better today. It's quite easy to understand in principle. So the boundary layer processes, they disturb our geostrophic balance in principle. That is what's happening. There's an additional force that disturbs our geostrophic balance in the boundary layer. And that is essentially what we want to derive today. So the way this can be easily done, the easiest way to do this, of course, as you have already understood, we always try to consider the most simple cases so we can treat things easily by looking and manipulating equations. Otherwise, the real atmosphere is really complicated. So we try to simplify always the systems as much as possible. So the equations become as simple as possible so we can easily understand what is going on. So again, we are using here something that is called the Boussinesq approximation, which for our case means that essentially we go back to the shallow water model. So we consider just the lower part of the atmosphere where maybe the density varies very little. Of course, that's not true if we really now go up to the high troposphere, but in the lower troposphere, that would be the case. Maybe the density is varying only by up to 10% or something like this. And so that means we can also use, again, the incompressibility equation. So we come back to our Euler equations that we have written down already many times from the very first lecture. And as you can see, there's no frictional term here, even though we think that friction should be the term that we are considering here. But as you can see, we could include a frictional term here, but that is actually not the main effect that is directly acting on the flow that we are looking at. And we will derive why this is in this course now. And then we have the incompressible condition, which is again the three-dimensional divergence is 0. So this exactly looks like our shallow water equations as it is now. Now, the Boussinesq approximation, I think you have discussed that already. You must have discussed that already in your atmospheric physics course. It goes much beyond this. In particularly, if you look at the vertical momentum equation, if we consider the Boussinesq approximation, we usually go beyond just assuming hydrostatic balance in the vertical direction. But there is we are considering first order deviations from the hydrostatic balance. And in that case, the buoyancy term comes into play if we look at the vertical momentum equation. Now, we don't need to consider this here. It's not relevant for the processes we want to consider here, but generally, that is part of the Boussinesq approximation. Also, this first order approximation in the vertical momentum equation, in which buoyancy terms come into play. But we don't need this here. We just don't have to consider this. We can deal with this without it and just assume for us that the atmosphere is even hydrostatic, in hydrostatic balance. Now, another term that you have already discussed, I'm sure of, in the atmospheric physics course, is the Reynolds averaging. Have you heard about Reynolds averaging? Now, the thing is, we want to understand the action of smaller scale eddies on the resolved flow. And this problem will always appear. If you write, if you in your thesis, in your PhD thesis or whatever, or later in research, you plan to write a numerical model, there's always a horizontal, vertical, and time resolution. And that means there will be always scales that you cannot resolve with that model. So you will always have to allow that there are subgrid processes that interfere with your resolved flow, because your resolved flow is only, if you write any numerical model, is only valid for some kind of grid cell. So if we have a grid cell, a not very nice grid cell, then our flow that we can resolve, we may say this is U bar. So that would be representative as mean value, let's say, for this grid cell. And we could say, okay, we are not interested in anything else, but that's not reality. In reality, there is motion that is smaller scale than this grid cell that we resolve, unless we go to really the molecular scale of or millimeter scale perhaps, but there will be always scales that we cannot resolve. And this is due to time and space discretization. But the same would be true if you just look at measurements. Measurements, they also have their time and space resolution due to the accuracy of our measurement instruments. So whatever data we look at, model data or observational data, there's always something acting on that scale that we measure or that we model that we cannot resolve. So this is probably a general problem that may occur. So this influence of the smaller scales fluctuations that in reality are there, but we cannot resolve on the scales that we are interested in. In order to do this, we simply say, okay, our total flow can be represented by this mean quantity that we can resolve, either in a numerical model or with a measurement, plus some rather unknown fluctuation. But we have to allow for this to be there, because we know we haven't measured everything. There is something we haven't measured, probably. And we can do this, in this case, for our velocity perturbations. Then if there's always also temperature, like if we look at the vertical momentum equation, then the buoyancy term and temperature perturbations could come into play, and we should also maybe consider what is happening if we look at temperature perturbations. But we don't need to do this here. Density is set to constant, so there's no other term. Now, it is commonly, the common treatment to do this is to write the advection term of a quantity, which can be, is in our case, either just the zonal or the meridional velocity, in a slightly different way. And the way we call this is the flux form of the advection term. So we can write down the advection, as you know, as the time derivative plus u d by dx plus v d by dy plus w d by dz of this quantity. But then we can simply use a trick we can add a zero. So A times the divergence is zero. So this is just simply adding a zero. So this is still valid. This is an exact identity. And if we combine these two terms using the product rule of differentiation, you can see that you can express the total derivative also in this what we call flux form. So we have the local derivative of this quantity here, plus the what we call convergence of flux of this quantity. And this convergence, convergence is a vector, and then there is a flux, and so there are three components that are multiplied in a scalar way, and this gives us these three contributions. So we could write this also as nabla scalar product, then A times the three-dimensional velocity in this case. So therefore, this is called flux, convergence of our fluxes. By the way, in this case, we have made use of this. The Reynolds averaging is based on the assumption that we have this three-dimensional divergence, which is zero, approximately zero. So we can use this trick here to derive the flux form in this way. But there's obviously an exact three-dimensional counterpart. And that you can easily show using the continuity equation that looks like rho dA by dt. So we have to then to carry our rho, our density in the compressible case. And that would be equal to d rho A by dt plus, and now again the convergence of, here's a scalar product, A rho and V. So that would be the exact form of this. But as we can say, as we can immediately see, this is the more generic form. So if density is constant, we can simply take this out of the differentials and divide by rho, and then we get back to our form here. But this would be the exact flux form. In principle, more complicated, because now if we don't use this Reynolds averaging, which is based on the fact that we have divergence-free flow, then we have a triple product here, which makes our treatment even more complicated if we have to take into account fluctuations of density. But there are ways around this also. So the thing now is, if we apply now our averaging operator to this equation here, then we can make use of now having this expression here. So we assume that averaging and time derivative and everything else we can exchange, it's exchangeable. But we have further to assume when we do this, when we apply the averaging to these flux terms, that if we have, of course, the average of average quantities expressed here, then that's just the product of these average quantities. And then if we have the average of our fluctuation quantities, which we have always ignored when we were linearizing our equations, but that is not the case here. This term is relevant, but then these mixed terms between average and fluctuations averaged, they are zero because the average can be taken out, and then the A primed averaged and B primed averaged, they are identical zero. That is the definition of these Reynolds averages. The average over a perturbation quantity defined as perturbation from the average has to be zero. We can immediately see this here. If we put an average here, right, then A bar is equal to A bar, of course. So that means that A prime bar has to be zero. Otherwise, this equation wouldn't be valid. So when we do the averaging of a product, the only term that survives is the product of the averages and the product of the prime quantities averaged. That means if we do this systematically to this equation here and insert for A, in one case, the u velocity, the zonal velocity, in the other case, the meridianal velocity, we get to this equation here, where we can write this, and this is intuitively clear for us. It's convenient now for us to write the total derivative that just depends on the resolved, on our resolved or measured quantities, or the quantities that we want to describe in our model. The only things that we can describe in our model, we collect them all. These are the mean quantities that we can resolve, that we can measure, that we can model. And they're collected here. But then there are these additional terms that we cannot measure, we cannot resolve. In our model, we don't have, there's no way we can model this straightforward, the action of these additional terms. But these additional terms are there. Now, either we could say, and this is, of course, done in the free atmosphere, for example, these terms are probably small. These terms can be small. And then we find, okay, if the flow is not accelerating, we have our geostrophic balance, for example. But in the boundary layer, it turns out that the boundary layer processes, having the roughness of a surface present, makes this interaction, makes this the small scale flows so powerful that they may disturb our mean flow. So they may interact with our mean flow. And this is, of course, an empirical evidence that we have to accept that this is the case. Now, we are lucky if we apply the averaging to our continuity equation, since that is a linear equation. So the reason why we have these nonlinear terms is that we have a nonlinear advection term. Otherwise, we wouldn't have these additional terms. So our nonlinear advection term is the reason for these additional terms. We are lucky that we have our incompressibility condition, because otherwise also this pressure gradient term could have fluctuations of density, and so that would be a nonlinear term, but that's not the case due to our simplification. And also the continuity equation becomes this simple equation here, just the mean equation. So the problem is now, if we want to solve our flow, we either assume that these terms are zero, which we may do, or we have to make an assumption for these terms. The simplest assumption is that they are zero, but if we find in our boundary layer, that is probably not a good approximation, because we see our wind, if we measure our wind, is not parallel to the isobars. So this geostrophic balance here is strongly systematically perturbed in the boundary layer. So there must be an influence from these terms. Now, having these terms is generally called as a very general problem in turbulence theory, and that is the closure problem. This problem is very well known as the closure problem in turbulence theory. And there are whole theories how we may now parameterize these as functions of the mean flow, because this is what we need. If we want to understand what's going on here, we have to parameterize all these terms as functions of our mean resolved measured or modeled quantities. Otherwise, there's no way we can understand what is the action of these terms on our mean flow. So we have to make some assumptions. And the turbulence theory provides hints how turbulence acts in certain geometry situations and in certain stability situations and so on. So there is a whole history of hundreds of years of research that try to find out how to best treat these terms. Now, one way, and that technique is used also in numerical weather predictions and in turbulence theory in general, and also in climate models probably, is that you can try, I just write down, and that is possible, knowing the full equations is possible, to write down equations for these second moments. So I've just used here one. You can write down equations for the quadratic terms appearing here. That can be u square, u prime square, that can be u prime w bar, and so on. If you do that, and you can do this using we know the equations, we can do this. We can write down equations, prognostic equations for these perturbation quantities. The problem is that on the right-hand side, we get triple products of these quantities. So there would be something like d by dx. That's always because of the nonlinearity of these equations. There would be something like d by dx, u primed, bar. And so the problem will never close. So if this was closed within the prime squared quantities, maybe you could find a closed system of equations, but it's not, because due to the nonlinearity of our system, we get triple quantities and so on. Then we can try to write equations for the triple quantities, and we get quadruple quantities for that equation. So this will never close. Now, but some turbulence theories suggest that it's maybe better to use a higher order closure. So you use a prognostic equation for the variances, or in this case, sometimes you call this in climate and weather prediction models, turbulent kinetic energy closure, because this represents then the turbulent kinetic energy if you include also the other velocity components. And then you try to parameterize these additional terms. So the equations become a little bit more complex. Now, it turns out for the most simple approach, we don't need this. So we don't need this, but we have to do something better than just saying that these are zero, because in the atmospheric boundary layer, they are not zero. There's a strong action on these terms. But it turns out we may assume to a very good approximation that these horizontal convergence components, they are close to zero. They are not so relevant. But it's this vertical derivative. So in the boundary layer, our kind of geometry gives us that it's the vertical direction that is particularly standing out here. So it's the vertical derivative. The flow is changing strongly in the vertical direction, but maybe in the horizontal direction, we can assume horizontal homogeneity. This is a very often used assumption also in turbulence theory. So, but these vertical terms here, they have to be parameterized. We cannot just say they are zero. But how we do this? One way, and that is the way that we will be using here, is that we are, oh, what about, this is the action of smaller scale eddies on the mean flow. What about if we think, oh, that could be similar to the action of molecular viscosity on small scale flow. What does molecular viscosity do? It tries to remove shear. It tries to remove all shear. And if we have a rigid boundary, it will make the flow zero in the end. This is what molecular friction does. It tries to remove changes in our flow. So we can say, okay, let's say the action of these fluxes that we parameterize here is the same as if we had a molecular friction. In molecular friction, we know, how to write that down. This is a well-known formula. And the way to do it is to say that the fluxes are proportional to a coefficient times the shear of our flow. So if the friction has managed to remove the shear, then those fluxes are zero. Then the frictional terms have reached their aim. They have removed completely the shear. There's no vertical shear in our flow. So this would be a parameterization consistent with molecular frictional effects. Now, the problem is that this Km term, this diffusion coefficient, we call this diffusion, momentum diffusion coefficient, we cannot derive this from first principles. Whereas for molecular friction, you can use first principles, statistical physics applied to Boltzmann equations and so on. So go back to very, very, very first principles of interactions of molecules in order to derive the values for the frictional dissipation term, depending on the material, on the fluid or the air that we are looking at. For our turbulence theory, this is not possible. So this term, Km, which by the way can also be a function of the vertical coordinate, can be a function of stability of our situation. So in unstable and stable conditions, there can be different terms and can be a function of the roughness of the surface. But we cannot derive this from first principles. We have to, let's say, measure it or find some simple relations to the roughness of our surfaces and so on. But it cannot be derived from first principles. So this is impossible. We will use a trick later how to derive what is a typical value for this quantity in weather prediction and climate models, for example. If this parameterization is used there, if you use another parameterization, then you will have to use another. Then there will appear another quantity. There are several ways how this is done in models, but one way is this. Okay, so we have simplified this now. If we do this, you can see we assume that these terms are nearly zero, and then we can evaluate these terms here. They will just be, since the right-hand side here is just a function of mean quantities, we have closed our system. Here the system is not closed because we don't know what these quantities are. But the fact that we can express these quantities, these fluctuation products, as functions of the mean flow means that these two equations, they can be closed. So that's what we will be doing now. And we call this layer where we want to apply this, the Ekman layer. where these frictional effects are so important to disturb our geostrophic flow. That is where we define our Ekman layer. Maybe not very close to the surface, not the contact layer, but this is this layer where our geostrophic flow that we have maybe at the top of this boundary layer is strongly influenced by these frictional processes in this layer. And of course, you can feel this if you, I mean, all of you have flown in an airplane. If the airplane is in the, maybe there's some free air turbulence too, of course. So sometimes the airplane is shaking, but in particular, we feel as the airplane comes down and enters the atmospheric boundary layer, you feel a lot of this turbulence. The airplane is kind of shaking. And so that is the action of these eddies that we are looking at now, that act on the mean flow and on the airplane. So one trick is now to reintroduce the geostrophic equations. So instead of using the pressure gradient here, we are using the fact that we assume in the free atmosphere, there will be geostrophic balance. So we can replace this by our geostrophic winds that should be applying in the free atmosphere. But there are several more assumptions here, because in order to get this set of equations here, we have also assumed that we are in a stationary state, horizontally homogeneous, so no horizontal changes of our mean quantities or our fluctuation quantities. And also we have assumed that the vertical advection term of the velocities is small compared to the other terms. So there should be, apart from our geostrophic, this would be our geostrophic equilibrium, the only term that is supposed to disturb our geostrophic equilibrium is this additional term. If the action of our friction on the flow is zero, then we have geostrophic equilibrium. The solution would be the wind is the geostrophic wind for both components. But the action of the turbulent eddies disturbs our geostrophic equilibrium in this boundary layer that connects the surface with the free atmosphere. So this is the set of equation that we want to solve in this lecture. This is easy, no? Linear. It's linear, and you have seen those equations before, because this is a diffusion equation. You have solved the diffusion equation in your numerical methods course, I'm pretty sure. Did you do this? Did you solve a diffusion equation? Not yet, maybe, because you didn't start yet numerical methods too. That will start later? Yes. This is a pity. But that is also good. So there, I'm sure you will, the diffusion equation is a very classical equation in physics that has very interesting properties. This is a type of diffusion equation because we have this second derivative here. There's no time derivative, but in an exercise that you will get at the end of this lecture, there is a time derivative. So if we don't have these terms, then that adding a time derivative here would lead us to the classical diffusion equation for the velocities. But we have these additional terms where we have the v component in this u momentum equation and the u component in the original momentum equation. We can almost guess that this could lead to some oscillation behavior, because this having these terms mixed often in equation leads to oscillatory behavior. Okay, now we want to go a step further. We want to solve this equation, but we have to have boundary conditions. So the boundary conditions that we want to use to solve these equations for our boundary layer is that if we go high up, we want to have that the flow is geostrophic. So V should go to Vg and U should go to Ug. And at the lower boundary, we want to have zero flow. So the friction should remove all the flow close to the boundary. That's what friction is supposed to do. These are our two boundary conditions. If we further assume that our geostrophic wind, which is proportional to the pressure gradient force, is independent of height, we can write this equation in terms of these star quantities. And the star quantities is the deviation in our boundary layer from the geostrophic wind. It's just a substitution of quantities. So instead of this system here, we can write it in this system here. And as you can see, we can write this Coriolis term, we can write as a matrix 0 F minus F 0 applied to U star V star. No, you can simply apply this matrix multiplication and you get back these two terms when you insert the U star in the definition of the V star. And so this becomes our equation, linear equation, a linear homogeneous equation. So perfect. We know how to solve this already. We have had those examples already many times when we linearized equations in order to understand the behavior of waves, when we looked at Rossby waves, for example, and so on. So we can assume that our solutions are of the form of an amplitude times some wavy behavior in the vertical direction. So there's a wave number in the vertical direction times that. There's no time derivative here. So there's not a real wave propagation that we consider here because we have assumed that we are in a stationary state. If we simply insert this and work out this derivative, which of course you know brings us the minus I square m square down, and then there's this parameter here, and then this just doesn't do anything, and then we divide by our amplitude and by the sine functions, by the exponential function here, then we get our matrix that we have had several times already. So our solution matrix for the dispersion relationship looks like this. A matrix applied to our amplitude vector A and B is 0. And remember again, we are looking for non-trivial solutions, right? One solution is always A and B is 0, but this is a trivial solution. We want to have non-trivial solutions. Non-trivial solutions we find by requiring that the determinant of this matrix is 0. Very easy to do. Determinant, this times this minus this times this. We get to this equation here. In principle, very simple, with the problem that we have a power of 4 here. So we get 4 solutions. And those 4 solutions look like, we concentrate here on positive F, which is would be the northern hemisphere. But everything can be translated also into the southern hemisphere. We get these 4 solutions. It's kind of tedious because it's too much. And so, there's also the problem, we get the square root of I here, but the square root of I can be replaced by some identity by this here. So we can simply express the square root of I here. Now we are lucky because we have assumed that our flow as we go high up should converge to the geostrophic wind. But there are 2 solutions here, M2 and M4. They go with minus I. So if we have something that is minus I times I, then I square is minus 1. So that would lead to something that grows exponentially as we go up in height. So the solutions M2 and M4, they don't decay to 0, but they grow. So we can immediately remove two of these solutions because they won't fulfill our boundary conditions. So only M1 and M3 fulfills our boundary conditions. Then you can do more things. You can insert this M1 and M3 in the original system of equations 208, which is this here, and find the two eigenvectors. You can simply solve them. These are the two eigenvectors. Now it turns out that these are also complex conjugate. That means they're not independent. That means we can either use x1 or x3, and then we have solved the equations already completely. So we can simply pick x1, but x3 would does this the same solution. So our solutions look now so M1 would be M1. So our U star and our V star, which is the deviation from the geostrophic wind, the solutions look like taking this 1 and I, A times e to the power of I, M1 and Z. Then we express the definition of this, but we have to assume that our amplitude function A is a complex number. And like in many physical examples, we are looking for the real part, we are looking for real solutions of this. So the real part, if we insert this complex number, then are just given by where we find the real parts here. So we collect all the real parts of the solution. And so our solution looks like this, with quantities B and C, which are unknown. And so we also have to have used this gamma quantity, which is F times 2, square root of F times 2 km divided by 2 km. But we have still to find what is A, what is B, and what is C. Now, these are determined by the boundary conditions. So the boundary conditions at Z equals 0 give us what is B and what is C. Because if we insert in this equation Z equals 0, the exponential just goes to 1. And we get two equations. This becomes minus UG, and this becomes minus VG. But the sign goes to 0. And so we can just identify, and the cosine goes to 1. So we come to the conclusion that B is minus UG and C is VG. So we can insert this here, having used these boundary conditions. This is our generic solution. So this is something that from the surface we go up that starts to rotate. That's a rotation in the vertical direction and a decay term. A rotation and a decay term. It looks like this. Actually, you start from 0. That was our boundary condition. The winds are 0. So this is some kind of idealized solution of this, assuming that the wind, the geostrophic wind has just a U component, no V component. And then you get this rotation. Now this rotation we hardly see because there should be some spiral. This is called Ekman spiral. But the decay is so quickly that you just see some kind of overshooting and then almost nothing anymore. But there is clearly a rotation of our winds as we go up. So as we go up, then the V component in this case becomes large. But then as we go further up, we have to converge to our geostrophic wind, which in this case was assumed just to be zonal. So this is how the solution looks like. This rotation of the winds. Of course, if we set, like in this example of the figure, if we set Vg to 0, the geostrophic wind, and we just say, okay, let's assume that our geostrophic wind has just a u component. Then this becomes a little bit simpler because this term is dropping out, and this term is dropping out, and this term is dropping out. So we get a much simpler formulation if we assume that. Now we use a trick. We want, of course, actually, what we want to identify is that what is the height of the boundary layer for this simple case of treating a boundary layer. Now, to estimate the height of the boundary layer is a whole science in itself. And there can be so many definitions, depending on, in our case here, just on mechanical considerations, just on things related to wind considerations. But in reality, boundary layer height could be dependent on the stability, of course, of our layer. So we may have to consider temperature, the vertical temperature distributions, and so on. But for our purpose, and this gives us a reasonable number, one good way to identify that boundary layer height is, oh, why don't we define the boundary layer height looking at this kind of spiral behavior, and then this does some rotation here as we go to the geostrophic wind. But we say once our flow has reached the first time and comes close to the geostrophic flow already, and then there's just some small perturbations from that. We define this is the height of our boundary layer. And so that would be when our flow is the first time parallel to the geostrophic wind. That would be when this sign here goes to 0, because then the wind becomes parallel to the geostrophic wind, because the sign drops out from these two equations. And so the sign of gamma z is equal to 0 tells us gamma z has to be, or gamma, this scale height, what we call d, the height of the Ekman layer, dE, has to be equal to pi over gamma, because then is the sign of this product becomes 0. Then gamma times dE is just pi, and sine of pi is 0. So that defines us the height of this boundary layer. And if you remember the airplane, that height is typically considered to be close to 1 kilometer. So on average, but of course that can vary. In the real world, this varies between, probably if you have very unstable conditions, the boundary layer, I mean, we talk about this often in current weather. It depends on, in reality, on the stability of the atmosphere. So the boundary layer height can be a few kilometers to very, very, very low, to a few hundred meters maybe, or even lower. But on average, let's say a typical scale for this height would be 1 kilometer. But if we insert this height here, then we can evaluate. The trick is then that we can, once we have inserted this height, this is 1 kilometer, we can, since we know F, if we are in the mid-latitudes or wherever we are, we know F, we can evaluate what is the value for this, for our exchange coefficient, Km. And this turns out to be kind of, for climate purposes, the typical value turns out to be around 5 meters squared per second for this quantity. Remember, we cannot derive this from molecular principles. This has to be somehow measured or derived from some other considerations. We cannot really determine this. It's a parameter that will be always, if we have such a parameter in our climate model or weather model, that is always a parameter that is uncertain to some extent. We don't have an exact handle of this. But okay, let's say we have some number for this value here. A typical number would be this. Now the aim of this whole exercise is now to say, okay, what is then the action of these perturbations of our geostrophic balance? Because this is what we have seen. The effect of this boundary layer friction was to disturb our geostrophic balance. So instead of having flow around a low pressure, and this is what we have seen in the picture, we have flow into the low pressure. And instead of having flow around in high pressure, we have flow out of the high pressure. So if we have the intuitive result is already that if we have simply a low pressure or a high pressure, where usually if we assume geostrophic winds, we don't have any divergence or convergence. We have just the rotational winds. But what these boundary layer processes do is they induce a convergence in a low pressure and a divergence in a high pressure. Now, formally, you can simply calculate this by calculating the divergence of our solution, du by dx minus dv by dy. So our convergence or divergence. If you do this using this solution, you can work out that there's one part proportional to the divergence of the geostrophic wind, and one part that is proportional to the vorticity of the geostrophic wind. Now, the divergence of this geostrophic wind, how we defined it, is always zero. This was the trick. That means that the final solution is that we get that an interesting, nice result. The convergence in our boundary layer is proportional to some vertical function times the vorticity in our free atmosphere. So whenever there is vorticity induced in the free atmosphere, then our boundary layer processes will lead to convergence or divergence, depending on the sign. And we now go a step further. We want to understand what is the vertical velocity we induce at the top of our boundary layer. So we can integrate our continuity equation vertically. We now have an expression for our divergence. So we can use the equations dw by dz equals to the divergence, integrate that vertically, assuming that the vertical velocity is zero at the ground. What is the vertical velocity induced by this convergence or divergence at the top of the boundary layer? So this divergence accumulates, and we increase our vertical motion. And that's a straightforward integration that you can use, that you can do using formula of the sine and cosine functions. And we get to this expression here. Because of this integration, there's 1 plus e to the power of minus pi. Now this e to the power of minus pi is around 0.1, because pi is 3 and this is around 3. So that gives us 3 to the power of 3. So this is about, or even smaller. Yes, this is even smaller than 0.1. So for the purpose of what we need in terms of accuracy, we can simply ignore this term. It's smaller than 0.1, as we said. So an approximation for this, for the vertical velocity on top of the boundary layer, is then that this vertical velocity is proportional to the geostrophic vorticity that may be induced by anything, divided by 2 gamma. And then you can express 2 gamma in terms of this exchange coefficient Km and the Coriolis parameter. Now, this is the important result of this lecture. We have shown that if we have a geostrophic vorticity, that may induce a vertical velocity in our system. And this is called Ekman pumping. So one example of Ekman pumping is, of course, if you have a cup of tea and there are some tea leaves inside, and you make a rotation, then in the end you will see that there's also something going on like Ekman pumping in your cup of tea, because there will be the tendency for your leaves to maybe come up. There will be some secondary circulation induced by the rotation that you have applied to your cup, induced by the frictional forces, and they will also cause the secondary circulation. Now we call this secondary circulation, that the circulation that is induced by the Ekman pumping mechanism. Now we just want to make an exercise here, a small exercise, because remember we have already derived an equation for the tropics that relates vertical winds to heating. And for our El Nino phenomenon, we have said, okay, if this equation is valid, then the heating, for example, induced by a sea surface temperature perturbation should be balanced by a vertical motion, because this is the most effective way to find an equilibrium in the tropics, because horizontal advection terms are so small. But this is just the diagnostic equation. So the way we will use this equation in the next lecture is to say, oh, it may be that in some cases we have induced a vertical velocity by Ekman pumping, and then that should be compensated by heating. And this heating must be related, or will be in most of the cases related to convective heating. So a vertical velocity in our induced by Ekman pumping could in some cases lead to convective precipitation. This is also clear if we have some lifting. We know already if we have lifting of our air parcels, that will lead to condensation and falling out of water, and therefore the air is heated on average. Now what we want to do is just to make a comparison of the order of magnitude of these terms. So it turns out if we insert typical quantities for geostrophic vorticity, which we have used also to do our scale analysis, typical values, we get to a quantity of the vertical velocity induced in for typical vorticity of Ekman pumping would be 2 times 2 minus 10 to the minus 3 meter per second. Now it turns out that this vertical velocity is actually comparable to a heating using this equation of 1 Kelvin per day, which for people who are investigating what are typical heating rate, this is actually quite a substantial heating rate. Maybe for ENSO, for an average ENSO event, you would have something more, maybe 4 Kelvin per day, but still this is almost in the same order of magnitude as a weakish El Nino kind of heating perturbation. So this shows us that Ekman pumping is potentially a very important mechanism to induce remote responses to El Nino, because we will see that the responses that we have remotely, they may actually be related to vorticity and therefore induce Ekman pumping, divergence, convergence, and vertical motion. Now, also in the ocean, you have Ekman layers. Actually, the ocean is more complicated because in the atmosphere, we have only one Ekman layer. But in the ocean, you can have two. One is at the bottom, for which the treatment is very similar to what we have done here. But the other is at the surface. But at the surface of the ocean, the boundary condition is different from what we have been using here. Because at the surface, there may be some wind forcing. And so what the action of Ekman pumping for the ocean at the surface, the treatment will be different from what we have looked at here, but you can also solve that equation. And I'm sure you will do this in your ocean course. You will probably solve this problem for these both cases, for the ocean surface friction, but more importantly, for many flows in the ocean, for the surface Ekman layer in the ocean. And we have also made already use of this when we said, okay, near the equator, we have the easterly wind stress. And due to ocean Ekman pumping, that will lead to northerly flow in the northern hemisphere and southerly flow in the southern hemisphere in the ocean, and that will lead to upwelling near the equator in the ocean. So we have made use of this already. Now for the exercises, the first two are just doing some calculation that are proposed for this lecture. The third one is more interesting. Now, the problem is that you have not probably dealt with this diffusion equation in your numerical methods course. I still encourage you to try to do this because it's very interesting. So the idea is to numerically solve these Ekman equations. You have solved them analytically, so we have the analytical solution, but we can try to solve them numerically by reinserting a time derivative and integrating so long until we find a stationary state. It turns out this will not take so long, maybe just a few days or less than that. Maybe 1 day is enough to integrate this equation. And then you will find a stationary state. So if the time derivative here is 0, then you have found numerically the solution. And the idea would be to compare that solution to the analytical solution. So how good is the analytical solution? How good is numerical solution compared to the well-known analytical solution? This is a very lucky case because often you will have the problem that you in future you will have to try to evaluate numerical solutions, how good they are. And the best way is to have an analytical solution. If you can compare your numerical solution with an analytical solution, then you can exactly measure the error of your solution. But there are only very few cases when this is the case. This is one very simple case where we have where we know the analytical solution of a numerical problem, for example. Now I encourage you to do this, to discretize this equation in space and in time, and to search for, to try to find the numerical solution. The analytical solution we know already. It's given in during this lecture. Now you could also, I know that you have now a Python course, right? So if you don't want to do this in Fortran, I think it would be very straightforward even to write a little Python code to integrate this equation in time after discretizing. Okay. If you can't do this now, we will come back to this once you have dealt with the diffusion equation in your numerical methods course. Because if you have done that, you have the code in principle, your numerical code is already ready. You just have to modify that a little bit. Because this is a real diffusion equation. If it wasn't for these extra terms here, this is the diffusion equation that you will be dealing with in the numerical methods course. So it's just a small complication with respect to our diffusion equation. And the diffusion equation, there is a time step criterion. The time step doesn't have to be larger than a certain number in order for your numerical integration to be stable. And so once you have worked that out, you can solve this equation. So that will be very interesting and plot it. It looks very nice. It's very nice. It's a very nice exercise. So either you try this now, or we will come back to this later on when you have dealt with the diffusion equation in your numerical methods course. So when is the numerical methods course 2 starting? Do you know? This is long from now, sometime in March.
I think next week.
Yes. So usually when I'm doing this exercise, the numerical methods course has already finished, because the numerical methods course 1 is usually done in the first term, and then also early in the second term. And usually students have already a code essentially to solve the diffusion equation. And then it's very straightforward just to insert these additional terms in the code that they have already. But anyway, if you are interested, it's fun to do this actually. Please do it. Okay, so tomorrow then we will make use of what we have learned today. So tomorrow we have lecture again at 11. And we will make use of this property of Ekman pumping to try to understand the mechanisms for tropical rainfall responses to an equatorial heating, for example, to a El Nino-induced heating anomaly in the atmosphere. So we will see that there are several processes that can be relevant for this remote rainfall adjustment. But Ekman pumping will play a very important role. Okay. See you tomorrow then. Stop sharing my screen. Bye.
Bye. Bye.